population genetics. Only 10 minutes. Population genetics. So what is the difference between Mendelian genetics and population genetics? बताओ, फर्स्ट क्लास में मैंने बोला था
Individual studies for Mendelian genetics.
Mendelian genetics, Mendelian is for individual level. Individual level. And this is for population level. Okay.
Population study.
Yes. Now we will see what is gene frequency. We will start with basic, that what is gene frequency. पता है किसी को? Suppose there are only two alleles. There are only two alleles. Please ignore that. There are two alleles, capital A, small a, at a particular locus. Then there and suppose there are total n diploid individuals. So the scenario will be capital A, capital A, capital A, small a, small a, small a. So this is what? Dominant. This is what? Heterozygous. This is what? Recessive. Okay. So I have written this DHR. Remember this: dominant, heterozygous, recessive. Okay. And this D plus H plus R will be total number of cases, that is capital N. Now we can say this capital A, capital A, capital A, small a, small a, small a, then D, sorry, this will be the frequency D, H, R. Now what is gene frequency? This is the proportion of genes in the group is called gene frequency. So proportion of genes. Now see, if I want to calculate the gene frequency of A, gene frequency of A, then what is the proportion of A? Tell me. See here, what is the proportion of A? This is
D by N.
No. A, see, A is here, capital A is also here. So I can write 2D plus H upon N. Because twice A is there, I am considering 2D plus H upon N, because there are A, capital A, small a. Or I can write it like D plus H by 2 upon N. This is okay. D plus H by 2 upon N. So this is equals to small p, gene frequency of A. Just like if I want to find the gene frequency of small a, so this will be, I'm writing R plus H upon 2 upon N, that is Q. R H by 2, why I am doing H by 2? Because there is A and A, both are there. So we will take half H by 2, H by 2. Okay. So this we have converted in P and Q. Now I'll tell you that P plus Q is equal to 1. The total gene frequency will be 100%, or we can say 1. How? See here, P is what? d plus h by 2 upon n plus r plus h by 2 upon n. So if I take an LCM, so this will be d plus h by 2 plus r plus h by 2. So this is what? D plus h plus r by n, and d plus h plus r is what? N. So p plus q is equal to 1. Okay. Now if in question means in exam the question can come like, if DHR is given and the number is given 402, 105 and 73, then what will be the gene frequency of A and what will be the gene frequency of small a? Then I can calculate P is equal to what? D plus H by 2 upon N. So D is what? 402 plus H by 2, 105 by 2 upon total is 580 N. So this will be 580. So too many questions can come from this part. Just like Q will be R
1 minus
plus
P.
H by 2 by N. I am right. Okay, that is also good. Then this will be 73 plus 105 by 2 upon 580. This will be 0.22, or I can directly count from 1 minus P, 1 minus 0.78. So this will be 0.2. Okay. Now suppose this is given in numbers. This proportion is given in numbers, that D is our this is what? D is what? D is representing what?
Dominant.
Dominant homozygous. H is heterozygous, R is recessive, and these are number, that 402 is dominant, 105 is heterozygous, and 73 is recessive. These are numbers is given. Now suppose if these three genotypes is given in percentage values, if the percentage is given like, then we will consider D plus H plus R is equal to 1. Instead of N, we will consider it is equals to 1 because our data is given in percentage. Then P will be D plus H by 2 because there will be N is equal to 1 and Q is equal to R plus H by 2. Now the question is given that 0.80, 0.20, 0.80, 0.20. It means there is no heterozygous. So what will be the P? P will be 0.8 plus 0. That will be 0.8.
0 by 2.
And Q will be 0.2. 0 by 2? No, 0 by 2. That only here D will be there plus 0. Okay. So this will be 0.8 and 0.2. Okay. Now this type of questions are there in your examination, that find the frequency, find this frequency if this dominant is given, heterozygous is given, and recessive is given, and we will cross check it with P plus Q should be 1. Okay. Now there is just 5 minutes. This, what is genic array? This is very important. Genic array or gametic array. किसी को पता है what is genic array or gametic array? किसी को पता है क्या? Okay. So suppose I am taking this capital A, small a, and its frequency is P and its frequency is Q. Then it is known as genic array or gametic array because these are gametes. If these are my parents, what is the gamete? Small, capital A. This is my parent, what is gamete? Small a. So this is what? Gametic array or xenic array. Now second one is xenotypic array. जीनोटाइपिक एरे, कभी कभी क्वेश्चंस में ऐसे डायरेक्ट देते हैं दैट इफ जेनिक एरे इज दिस व्हाट विल बी द फ्रीक्वेंसी, गेमेटिक एरे इज दिस व्हाट विल बी द फ्रीक्वेंसी if genotypic array is given. So genotypic array is, remember that this is the whole square of gametic array. Gametic array whole square. See, if I put simply capital A plus small a whole square, then this will be capital A, capital A small a, and this will be twice and small a, just like a plus b whole square. So this is what? Genotypic array. Okay, समझ में आया? Is there any doubt in this introductory part of population genetics?
सर
Yes.
सर जो हम यहाँ पे पी और क्यू कर रहे हैं, क्या इसको हम प्रोबेबिलिटी बोल सकते हैं? क्योंकि ये 1 से ऊपर तो जाएगा ही नहीं।
Yes, probability ही है ये। प्रोपोर्शन क्या होते हैं? प्रोबेबिलिटी ही होते हैं।
हाँ,
It is the probability of what? It is the probability of dominant, probability of heterozygous, probability, or we can say proportion. Proportion is better term to explain this. Okay, so this is our introductory part of this. In next class, I will start with Hardy-Weinberg law, and its properties are there and all. Okay, so I am stopping here. Just what?
PDF अवेलेबल करा दीजिए।
Okay, I'll send it to the group. Okay, then. See you. Okay, so in last class I have completed that the Mendelian genetics portion, and now we will start the population genetics, and in which I a bit introduced that day. So basically, population genetics studies the hereditary phenomena on a population level. So in that we will we will start with the gene frequency. And that assume that there are only two alleles, that is capital A and small a, at a particular locus. Now suppose there are n individuals, so I will write D, H and R. D is for dominant, H is for heterozygous, and R is for recessive. And this is capital A, that is our dominant homozygous. Heterozygous is capital A, small a, and this is recessive homozygous, that is small a, small a. Now we will say that all the three dominant plus heterozygous plus recessive will be our total n. So D plus H plus R is equal to capital N, that is the total of dominant type, heterozygous type and the recessive type. So three type of individual in group. So three type of individuals are capital A, capital A, small a, and small a, small a. And there are only two type of genes. That is capital A and small a. So with these two type of gene, there are three type of individuals. So if I am having capital N individuals, so how many genes will be there? Twice N genes will be there. Okay, if there are N individuals, see here, there are means one gene, two gene, three gene, four, five, six. So three individuals, three N is equal to three here. So three individuals are there. So twice N genes will be there. Okay. So double, that will be double genes will be there. Now, so I can write that capital A, there will be two A genes. Capital A, small a, there will be one capital A gene and one small a gene. Similarly, for a, there will be two small a genes. So the total number of A genes, if I want to find the total number of capital A genes in this group will be how much? 2D plus RH, because we have written as DHR, that is capital A, capital A, small a, small a, small a. So 2D, from there are two capital A and there is one H. So 2D plus H, there will be total number of A genes in that particular group. Now therefore, if I want to find the proportion of A, proportion of gene A. So proportion of gene A is the total number of A genes. If I write the in the formula ways, that total number of A genes divided by total number of genes. So total number of A genes is 2D plus H and total number of genes is 2N. So this will be 2N. So this will be 2N, and we have denoted that the proportion of gene A is P, small p. So I can write the P is the frequency or proportion of gene A, that is D plus H by 2 divided by N. If I divide this thing with 2, so this 2D, it will change in D plus H by 2 divided by N. So this is my P. Now this proportion is known as gene frequency of A. Gene frequency of A is P. Okay, so similarly we will calculate the gene frequency of small a, just like I'm not writing completely now. Similarly, total number of A genes will be total number of A genes in the group. How many it will be? It will be 2R plus H. Okay, because two recessives are there and one small a is there in the heterozygous. So 2R plus H. So proportion will be 2R plus H divided by 2N. Okay, I can write it R plus H by 2 divided by N. So this is my Q. R plus H by 2 divided by N. Okay, and we know that P plus Q is equal to 1. Now you can just prove this by putting this P and Q values. It will come 1. Now we will take one example in means ARS prelims or NET exam. This type of questions are there. That suppose there are 40 individuals in a particular population, and it is given as DHR, and it is given as 2, 12, and 26. Now what is the P and Q? So the proportion P is equal to D plus H by 2 divided by N. So D is what? 2, and H is 12. H 12 by 2 is 6 divided by 40. So 8 by 40. So it will be 0.2. Okay, this, so the gene frequency of A or P will be 0.2, and directly we can calculate that Q will be 0.8. Or if you want to check it, then you can check with R plus H by 2 divided by N. So R is what? 26 plus 6 divided by 40. So this will be 32 divided by 40, and this will be 0.8. Okay, so this, when these are given in numbers, so then we will use this DHR for formula, and we will use that P is equal to D plus H by 2 divided by N. But if in the question 3 genotypes are given in percentage, so this N will be 100, means it is given in percentage, so N will be 1. So D plus H plus R will take as 1. So P is equal to will be D plus H by 2, and Q is equal to R plus H by 2. Okay, so example is 0.05, 0.30, and 0.65. And so my proportion will be P is equal to D point, that D H R 0.05 plus H by 2, means 0.3 by 2, that is 0.15. So what will be the proportion? P is equal to 0.20 and Q will be 0.80. How? That Q is equal to R 0.65 plus H by 2 0.15. So we will add and we will get 0.80. So this type of question, basic question, can come in the exam, that calculate the what will be the P in case of this population is given and number of individual is given, that, or if it is given in percentage, we can calculate like this. Okay, any doubt in this? I think there will be no doubt. It is very simple. Now we will move to the random mating. Random mating, or it is known as, other name is panmixia. So other name of random mating is panmixia. So in case of bisexual organism, any one individual of one sex is equally likely to mate with any individual of the opposite sex. So that is known as random mating. Suppose this is known as random mating. Suppose this is a population, and these are the number of individual. This is for just I am taking for female, and this is male. But in human there is no random mating. But in plants and in other small organism, animals, there is random mating. So suppose this, for example, I am taking just for humans. So this is a population, and now in case of bisexual organism, so in case of bisexual organism, any one individual of one sex is equally likely to mate with any individual of the opposite sex. Okay, so suppose so this one female is equally likely to mate with this male, this male, this male, likewise any of the male with that population. Similarly, so this is known as random mating. Okay, so this type of matings are known as random matings. So if the mating is completely at random, if the mating is completely at random, so in the population, the frequency of AA, so suppose if I write that DHR is my population, and there are this is dominant, this is heterozygous, and this is safe, and it is completely random, then the frequency of AA, this cross AA cross AA will be D square. How we will make this? Now this, and the random mating population is known as random mating population is known as panmictic population. What is panmixia? Random mating is known as panmixia. What is random mating population? That is panmictic. Okay, so in some examples you will get that there is one panmictic population. What is the meaning? That is random mating population. Okay, don't get confused. Now how we will make this? We will take this, suppose I am taking here male and female, and this is my capital A, capital A, capital A, small a, small a, small a, and same here capital A, capital A, capital A, small a, small a, small a. So all these three type of individuals have equally likely probability to mate any of them. So AA can cross with AA also, so we will get D square. Okay, D into D square. AA can cross with capital A, small a, so their probability will be DH, and capital A cross can be crossed with small a, so this will be DR. Likewise, I can write here HD, H square, HR, RD, RH, and R square. Okay, so this is what this we have make a table, or we can say square of the all possible random matings. Now we will move to one important law, that is you might heard that Hardy-Weinberg law. किसी को पता है what is the Hardy-Weinberg law? Can anyone tell me what is Hardy-Weinberg law? What is an Hardy-Weinberg law? Okay, so we will consider here a large random mating population. We will consider a large random mating population. Large random mating population, or we can say it's as a large panmictic population. Large panmictic population with this is the P is the gene frequency of A, and Q is the gene frequency of small a, and P plus Q is equal to 1. Then I can write D is equal to P square, H is equal to 2PQ, and R is equal to Q square. Isn't it? I can write this D is equal to P square, H is equal to 2PQ, because see here DHR, and if we write this p square, 2pq and q square. So I can write again p square plus 2pq plus q square is also a 1. Sum of all three, because d plus h plus r is equal to 1 if the frequencies are given in percentage. Then, so the statement of this Hardy-Weinberg law is, in a large random mating population, in a large random mating population, gene and genotypic frequencies, remain constant from one generation to another generation in absence of systematic forces like, what are different systematic forces? Like mutation, migration, and another one, mutation, migration, and selection. So these three forces we will consider it later. Now see that this is the definition of Hardy-Weinberg law, that in a large random mating population, gene and genotypic frequencies will remain constant from one generation to another generation in the absence of these systematic forces like mutation, migration, and selection. So there should not be these type of forces like mutation, migration, and selection. So the genotypic proportions in next generation will be same as those in preceding generation. So these genotypic proportions, the 2p square, 2pq and q square, this will be same in generation to generation. Now the population p square, 2pq, q square is then said to be this. Then it is said to be, suppose this is my population and these are the frequencies. This will said to be in equilibrium. Equilibrium. So this is that p square, 2pq and q square, it's said to be in equilibrium under the system of random mating. So if the gene and genotypic frequencies remain constant over generations, then we can say that this population is in equilibrium. Okay. Now genotypic frequency are determined by gene frequency, which I have told you that genotypic frequencies, because this is my genotypes, capital A, capital A, capital A, small a, small a, small a. This will be determined by gene frequency, that is capital A, small a, and the gene frequency of A is P and gene frequency of small a is Q. So whenever we will take the square, suppose I am taking this square, then this will be P square, 2pq and Q square. Okay, so this is our first statement, that genotypic frequency is the square of gene frequency. So I can write genotypic array is equal to xenic array square. Okay, or gametic array. Now see, we will see. I'll just prove this Hardy-Weinberg law. Should I do it or not? Just tell me if you can do it, or if I explain, just tell me, because I have to make all the meetings and all. Okay, just one time I will do, and again I will skip. Now see here, to prove the Hardy-Weinberg law, we will see that type of meetings, then frequency of mating, then third one is offspring. Okay, so type of meetings are capital A, capital A. You write here, it's, we will see here AA, capital A, small a, small a, small a. So all possible matings we have to do. So capital A will be, can mate with capital A, can mate with capital A, small a, it can make it small a, small a. So there are three individuals, so there will be nine all possible combinations. So again, small capital A, small a can mate with capital A, capital A. Capital A, small a can mate with this capital A, small a. Capital A, small a can mate with small a, small a. And last one, small a cross with small a, small a. Okay, so these are the type of matings. Now we will see that their gene frequencies. We will see now gene frequency. So we know that D is equal to P square, H is equal to 2PQ, and R is equal to Q square. Okay, so see here, that is, I can write it's D square, because I have remembered this square I have made earlier, D square, DH, DR, HD, H square, HR, RD, RH, R square. All possible, what all possible type of matings. So I can write it D square, or I can write is P to the power 4. Okay, now homozygous is crossing with heterozygous. So we will get what? DH. DH. And the D is P square and H is 2PQ. So this will be 2P to the power 3Q. Okay, similarly capital A cross small a, small a, then this is D, this is R, so we will get DR, and the frequency will be P square Q square. Okay, then we have completed till yet, till this, all the three possible combination. Then capital A, small a cross capital A, capital A, so this will be HD, this will be HD. So HD will be 2P to the power 3Q. Okay. Similarly, capital A, capital A, capital A, capital A. So this will be H square, and this will be 4P square Q square, because H is what? 2PQ. Then next one is capital A, small a, small a, small a. That is heterozygous H into R. So I can write HR. So HR will be 2PQ to the power 3. Then next one is small a, capital A, capital A. Just small a cross capital A, capital A. So this will be R into D. So I can write RD. So R is what? Q square, and D is what? P square. So I can write it P square Q square. Then next one is small a, capital A, small a. That is R into H. So RH, H is what? 2PQ and R is Q. So this will be 2PQ to the power 3. Then last one is R square and this will be Q to the power 4. Okay? किसी को कोई doubt? Is there any doubt in this? Okay. So now in offspring generation, we will make this capital A, capital A, capital A, small a, small a, small a. See here, from this cross, which type of offspring we will get? Gametes will be A. Here gametes will be A. So we will get only capital A type. So all this frequency will go in this class. So this will be P to the power 4 and I will make dash here. Now see DH, it means we will get dominant as well as heterozygous. So we will take the half of this in dominant and half of this in heterozygous. So P to the power Q, this PQ, Q. Okay, this type of offspring will not come here. Now next is DR. So DR is there, then D is what? Our dominant, then PQ will be there and R, that will be PQ will be there. Sorry. So this will be DR, means C cross of A cross AA. So here the gametes is A, here the gametes is small a. So we will get heterozygous, isn't it? So A into A, only heterozygous we will get. So the all probability will go in P square Q square. Okay. The next one is capital A, small a, capital A, small a. So we will get heterozygous as well as dominant. So again we will make it half for both the population and there will be no. Then next one is capital A, small a, capital A, small a. So here we get all three type of combinations cross AA. See here two type of gametes, here also two type of gametes. We will get capital A, we will get capital A, small a, we will get capital A, small a, and we will get small a, small a. So this is the ratio 1:2:1. So here we will make it into three parts. So one is P square Q square, one is 2P square Q square, and one is P square Q square. Okay, the sum will be this. Now next is capital A, small a, small a, small a. Then we will get only this two type. So we will make it PQ to the power 3 and PQ to the power 3. Similarly, capital A, small a cross capital A, we will get only heterozygous type, P square Q square. Then this will be dash. Next is RH, means we will get both type. Oh, so this PQ to the power 3 and PQ to the power 3. And last one is Q to the power 4. Okay, got it? Is there any doubt? How we are breaking this? If is there any doubt, you can ask me. Now, for offspring generation, we will calculate that frequency of AA in next generation in offspring. So frequency of AA will be, we will add these four values, all the four values. So this is P square, P to the power 4 plus pq to the q plus pq q plus p square q square. Okay, now suppose I have taken p square as a common, so here we will remain with p square plus pq plus pq plus q square. So this is what p square, and p square plus 2pq plus q square. Now see what is this? This is 1. So we are remaining with p square. So we can say that we have started our means in initial generation we started with p square, and in next generation we are also getting p squared. So we can say that gene and genotypic frequencies are remain constant from generation to generation. Now you can also calculate for capital A and small a. That is I'm not doing. So by doing the sum, we will get here 2pq. So this will be p square 2pq and q square sum. So we can say that in next generation, the frequencies are same, p square, 2pq and q square. Okay, without, is there any doubt? Okay, so this is with 9 different kind of meetings. These are 9 meetings, but I can reduce into 6 meetings also. How can we reduce it? For example, suppose now if I combine, suppose I have if I combine this combined reciprocal crosses, the 9 different kinds of matings will change into 6 type. So this question can come in exam, that if we combine all the reciprocal crosses, then how many type of matings will be there? So there will be 6 mating. Now I will tell you how. See here, these are 9 different type of matings. Okay, so suppose this is, see here, this is my DH and HD. So this is what? Reciprocal crosses. Similarly, HR and RH. This is also reciprocal. Okay, now if I combine all these, so we will remain with 6 matings. See this is one another case, DR and RD. So this is my first, second, third, fourth, and fifth, and sixth. So we will remain with 6 matings if we combined our reciprocal crosses. Okay, समझ में आया? So, and the same procedure will be there. We will make all type of matings. So all type of matings will be capital A cross capital A, capital A, capital A cross capital A, small a, capital A cross small a, 3, and then we will make capital A cross capital A small a, and capital A cross small a, and small a cross small a, small a. So these are 6 type of matings. So same we will write this frequency of mating, then this will be p to the power 4, and there are 4pq, because there are 2 types of same matings. See, earlier it was 2pq into q, but I am writing here 4p to the power 3q, because there will be 2. Same, this will be 2. Same, this will be 2. So this type, if we combine our reciprocal crosses, then we will get this type of 6 matings. Okay, got it? So this is important question. If we combine our reciprocal crosses, then how many matings will be, how many random matings will be there? So there will be 6 matings. Now next one important thing is that the suppose initial population is not in equilibrium, then how many generations required for the equilibrium? So how many generation required for coming in equilibrium? Okay, so suppose for example, our initial population like capital A, capital A, capital A, small a, small a, small a, and these are the frequency DHR, and we know that P is equal to T plus H by 2 and Q is equal to R plus H by 2. Suppose this is not in equilibrium. This population, this is initial population is not in equilibrium. Then again we will make a type of matings and frequency and offspring. So on the basis of this general symbols, I will make all the matings, all the 9 matings or all the 6 matings, and I will get these frequencies like D square, DH, DR, HD likewise, and we will means bifurcate this D square and all. Half DH will be there likewise, and then we will calculate the gene frequency of AA in next generation. So we will get that D square plus half DH likewise. Then we will come to know that this will be D plus H by 2, and I can replace it with, and whole square will also come, so I can replace it with P square. So we can say that only one generation is required. So this question is this question came in one time in ARS examination, that how many generation, if the initial population is not in equilibrium, then how many generation will require to get in equilibrium? So there will be only one generation required. Okay, next. There is one important statement is also there, that random union of gametes is equal to random mating of individuals. So I remember it with like RUG, random unit of gametes, is equal to random mating of individuals. So you can remember with this, RUG is equal to RMI, that is random union of gametes is equal to random mating of individuals. What is the meaning of this? So instead of, I made that 9 classes, isn't it? I made 9 classes, and then I calculated frequencies for all the 3 offspring. But we can use this theorem that random union of gametes is equal to random mating of individuals. So instead of random mating of large population, now suppose I have a large population, then I have to make all possible random matings. So better to use this concept that random unit of gametes is equal to random mating of individuals. So what is the means concept here? So random union of gametes. See here, random union of gametes. See PQ. PQ. Suppose this is male and here female. And this is capital A, small a, capital A, small a. So what is this? These are my gametes. So this is random union of gametes. So in next this will be capital A, capital A, capital A, small a, small a, sorry, capital A, small a, and small a, small a. See the frequency of capital A in next generation is p square. Okay, and this will be 2 type. So this will be 2pq and this is q square. So in by making this random union of gametes, I can get random mating of individuals. ओके समझ में आया ये कॉन्सेप्ट? Get it or not? So instead of making this whole complete table 9 combination and then calculating this d square is equal to p to the power 4 to pq and then again calculating again adding, then we will get p square to pq q square. So just we will use the concept of random union of gametes. So then this is my initial population's gametes and I will get in next generation capital A, capital A, capital A, small a 2 times and small a, small a. So this is random mating of individuals in next generation. So this is the concept which is very much useful for the large random mating population. Now we will see properties of the equilibrium. Properties of equilibrium population. So first property is, I told you this is genotypic array is equal to gametic array square. And second one, this concept is also same just like random union of gametes is equal to random mating of individuals. Then second is proportion of heterozygous, that is H is equal to 2pq, never exceeds 0.5. What is the meaning of this statement? That proportion of heterozygous, that is H is equal to 2pq, it will never exceed 0.5. It means that if we have some population and we will calculating this p square 2pq and q square, so this proportion will not be more than 0.5, never. It will never be more than 0.5. So it can be less than 0.5, but it cannot exceed 0.5. How we will check it? See, what is H? H is equal to 2pq. Now if I replace 2p and q is 1 minus p. So this will be 2p minus 2p square. Now if we see that by using the this derivative dh by dp for the maximization problem, So this will be 2 minus 4p. If I put is equal to 0, then 2 is equal to 4p and p is equal to 2 by 4. That is 0.5. So this is the maximum frequency of this capital A. This is maximum value. इससे ज़्यादा value नहीं हो सकती है p की. That is 0.5. So this is maximum value. So I can write the h is equal to 2p 1 minus p. So this will be 2 into 1 by 2 into 1 by 2. So this 1 by 2, this cancel, that is 1 by 2. So this is h max. So maximum value can be 0.5. So h cannot be greater than 0.5. Okay. So the statement is proportion of heterozygous never exceed 0.5. Now, why this is very much important? Whenever you have some question in the examination or some these frequencies, and you are suppose by mistake, by calculation mistake, that you have calculated that 2pq is coming your 0.7. So that is wrong. Sometimes it happens that p square q square and total is 1 is coming, but it is 0.7. Now in question it can come that question like, for example, that which population is in equilibrium. So there will be option like 0.2, 0.5, 2.5, 5 7.3. Second is 0.1, 0.7, 8.2. C is 0.3, 0.4, 0.3. D is 0.4, 0.1, 0.5. So this type of question can come. So here see, like directly I can say that this is wrong because 2pq cannot exceed 0.5. Okay. Are you getting this point? So this type of question can be there, that which population is not in equilibrium, is not in, because their 2pq is never exceed 0.5. Now next property, that ratio of heterozygous means ratio of heterozygous to the square root of both the homozygous, that is D and R, and that is constant, and the constant value is 2. So I can write is h is equal to 2 under root dr, and I can write h square is equal to 4 dr. So this is also an important result. So the ratio of, I can write the statement, ratio of heterozygous to with square root of both homozygous is constant, and that is okay. So this is h square is equal to 4 dr. Now this property offer us a simple test for equilibrium. So this will be useful to check equilibrium. If this ratio is not coming to, then we can say that there is problem. Suppose I have made this example arbitrarily, so हो सकता है कि this is not in equilibrium by this also. So just let me check. If I take option 1, so this is 0.5 divided by under root dr. So under root dr will be like 0.2 and 0.3. So likewise we can calculate. So this will be 0.6. So it is not coming like constant. This is not coming 2. So we can say this is also not in equilibrium. But I told you this example on behalf of this H is not equal to 0.5. Okay. So this can be also in not in equilibrium. Just I have made the example arbitrarily. Now, so this H square is equal to 4dr is used to check the equilibrium. So ratio of 2 is independent of gene frequency. So this ratio means 2 is independent of any of the gene frequency. So this ratio should come 2 when we have to check the equilibrium. Now I can say that any population that is DHR may be represented by a point in an equilateral triangle. Equilateral triangle. Suppose this is my equilateral triangle. What is the meaning of equilateral triangle? Tell me. What is the meaning of
All sides are same.
all sides are same. So suppose I have taken this y, x and z. You know what is altitude in this triangle? Anyone know? What is the altitude?
If we draw a line to the base at 90-degree angle,
So this YO is the altitude. Means if we make this, if we draw a line from the vertex by to the downward, so it will come in, I think, in middlemost value. So I just missed that middle value. So this YO is known as altitude. So now see here, and this D and HR will, this will be make, this will make a 90-degree angle. So if I consider this edge D, this is H and this is R, and this is some point P. So that D plus H plus R will be equals to altitude. This will be equals to our altitude. So this is equilateral triangle. So we can say that point in equilateral triangle. So this is point, and this all three are our D, H and R. So that is just for representation. Now next, one important question is in here. Suppose this is a point and this is making this is H, this is D, this is R, for example. Now I told you this H square is equal to 4dr. So this h square is equal to 4dr will make a parabola. This will make a parabola. So the question is on question is parabola. So it can come in your exam that what which type of curve can be made by h square is equal to dr 4dr. So the answer is parabola. Okay. So by this, any equilibrium population correspond to the point on a parabola. So any of the population which is in equilibrium, it will come on this parabola line. So this is important question that you remember, just that h square 4dr will make a parabola. Now next property, that h will not greater than to the d plus r. What is this meaning? That the frequency of heterozygous will never exceed to the sum of frequency of d and frequency of r. So this is also a case that frequency of heterozygous will never exceed to the sum of d and r. Now next property, if gene frequency of one gene is greater than twice the gene frequency of another gene. For example, if P is greater than 2Q, if one gene frequency is greater than twice the another gene frequency, then this P square 2PQ and Q square, then the heterozygous will be intermediate. So see, this will be intermediate. So what is the statement? If one gene frequency is greater than twice the gene frequency of another one, then this heterozygous will lie between two. The frequency of, for example, just I am taking arbitrarily, suppose P is equal to 0.5 and Q is equal to 0.2, for example. So this is twice, means see here, if I take 2Q, so this is what, 0.4, and 0.4 is greater than 0.5. So this is P greater than 2Q. Then this 2PQ, so 2PQ, 2 into P is 0.5 and Q is 0.2. So 0.2 into how much it will be, 0.01, isn't it, into 2, that is 0.02. So this will be intermediate of this. So P square will be 0.25 and Q square will be 0.04. So see here, this is intermediate. Is it right or not? 2 into 0.5 into 0.2. So 1, I think it will be 0.2. And okay, 0.2 is this will be 0.20 na?
Yes, sir.
Will
0.2.
be
0.2 only, sir. 2PQ value.
yes, 0.2, and this will be Q square. Q square, and Q is our 0.2 into 0.2, that is 0.04. Yes. So this will be intermediate of this. Hence we have seen that if the gene frequency of one is greater than twice the gene frequency of another, then this heterozygous will be intermediate. The frequency of heterozygous will be intermediate of this. Similarly, if we take the just opposite, that Q is greater than twice of P, then this will be Q square 2PQ and P square. Okay, similar, same thing. So these are the properties of equilibrium of the in population. So if some population is in equilibrium, so these properties will lie there. So all the property will be there in this population. So for that, if I want to check that particular population is in equilibrium or not, so this property should follow. These 5 or 6 properties are there. Okay, is there any doubt in this Hardy-Weinberg law? Is there any doubt in Hardy-Weinberg law?
No, sir.
Okay, so now I will take 5-minute break and will continue. Wait for this 5 minute. Just for refreshment. Okay. So with this we have completed. Am I audible? Okay. So with this we have completed our Hardy-Weinberg law. Now we will see another means another thing like sex-linked inheritance. This is also an important topic. So sex-linked. Who can you tell what are the sex-linked gene?
Baldness in males.
Huh? Gaurav. I didn't get you.
Okay. Actually, sir, I told characters, sex-linked characters. Sex-linked genes are X and Y. Here.
Hello. My voice is there or not? Hello.
Yes, sir. Audible.
Am I audible? Yes. Okay. So sex-linked genes are that the genes that are located on sex chromosome. The genes that are located on means the chromosome which is useful to determine the sex of like male or female. Okay, so like we can say that homogametic type that is capital X capital X. So this will be female, and heterogametic type capital X Y. This will be male. So we can say that X is our sex chromosome because if there are two sex chromosomes, then we can say this is female. If there is only one sex chromosome, then we can say this is male. So this is the representation of female and capital X, and this is the representation of male, and this is capital X Y, and there will be two sex chromosome, and there will be one sex chromosome. Just a minute, huh? I have a call. Okay, so there will be these two sex chromosomes. Now we will see that equilibrium in sex-linked genes. So there will be two cases. Now question is same question that in how many generation how many generation required for to attain the equilibrium. So case 1, there will be two case. That case 1 is when gene frequency of female and male is same. Like this is, if I, this is my male, then this is PQ and this will be our female, because there will be two sex chromosome. So this is P square 2PQ and Q square. So these frequencies are same here in both the sexes, like male and female frequencies is same PQ. Then such population will be equilibrium in one generation only. So that, like we will say that for female, how we will check for female? Again, we will make type of mating, then frequency, then offspring. Okay, that is capital A, capital A, capital A, small a, small a, small a. Type of mating will be like capital A cross capital A, capital A, capital A cross capital A, small a, capital A cross capital A, sorry, small a, small a. Just like small a cross capital A, capital A, small a cross capital A, small a, and small a cross small a, small a. From here, we will make crosses. Okay, all possible crosses. Now we will make the frequency. So this will be PQ and 2P square Q. Likewise, we will make all the frequency. Then we will bifurcate all these three in the offspring. Then we will sum this, and we will get that in next generation this is 2P P square, 2PQ and Q square. Okay, so this is all about your female parents. So this, we can say that we started the female gene frequencies. We started with female gene frequency like P square, 2PQ and Q square. And in next generation, we also get same probability or same gene frequency in next generation also. So we can say that this population came into the equilibrium in only one generation. Similarly, for male offspring, we will write here Y and here XA P and X small a Q. So we will remain with XAY, X small a Y. So the probability will be P and Q here. So we can say that we start with PQ and we will get in next generation PQ. Okay, so this we attain the only one generation required for the equilibrium to attain. Now case 2. Just wait a minute, this blank pages are finished, so I will share another screen. Okay, just be with me. Let it. Okay. So now case 2. So case 2 in which male and female will have different gene frequencies. For example, a capital A small a is suppose is having PQ, and this is my male, and this is female capital A capital A capital A small a small a small a. Then this is R, 2S and T. For example, I have taken these frequencies, and this is for female. So in next generation, and we can say the such that P plus Q is equal to 1 and R plus 2S plus T is equal to 1. Now, so gene frequency of A of female, gene frequency of A of female will be what it will be? Tell me, anyone? Can anyone tell me what will be the gene frequency of A of female?
R plus S.
R plus S. Similarly, gene frequency of small a of male, this will be R plus, sorry, S T plus S. Okay. Now to find out the proportion of genotype in next generation, we can use the principle that I told you, that random mating of random union of gametes is equal to random mating of individuals. What is his meanings? That see in next, this is my capital A small a of female, and suppose this is male here, capital A small a, and the gene frequency of male is PQ, and gene frequency of A, this is R plus S and T plus S. Okay, so these are the gametes of male and female. Now I will make it cross capital A capital A capital A small a capital A small a small a small a. So we will get random mating of individual for the next generation. So this will be capital A capital A capital A small a small a small a. So see here, what will be my frequency in next generation by using this? This will be P into R plus S. This will be P into T plus S. This will be Q into R plus S. This will be Q into T plus S. Okay. So in next generation, I will get next generation female. So I will get here P R plus S, P T plus S plus Q R plus S, and in of this R Q T plus S. So this I will get in next generation for the female, and for male we will get like A small a and Y. So this will be R plus S and T plus S. So this will be AY small ay. So this will be R plus S and T plus S. Now, can you make any interpretation of this? We can say that male is completely defined by or determined by female. See, gene frequency of A R plus S and gene frequency of small a is T plus S. So in our previous generation, this is my previous generation. This is my previous generation. So what is the gene frequency of female A? That is R plus S. And in next generation, we are getting the same gene frequency of capital A of male. Okay, are you getting the point? So this is the important statement that male is completely defined by or determined by the female in next generation, and female is determined by, so completely determined by female, and I can write it is parental generation, and determined by both male and female. So these are two important statements that male is, or we can say this will be the average of the both. So this is important statement that male is completely determined by the female and female is determined by both male and female. So with this we can make a few important results. Let me make this some results, like these are generations, and next is gene frequency. So generation and gene frequency of male and female. Now if I consider first generation as grandparent, and I just means I'm just, don't confuse with P and Q. This is another thing. Just I am replacing it Q double prime for grandparent, and this is for parent, and that is Q prime, and for offspring, that is Q. So this is male. We can write Q double prime X and Q double prime XX. This is Q prime X, Q double prime X, QX, Q double X. So these are general. I have made this table for 3 generations: grandparent, parent, and offspring. And this is my general overall frequencies of male and female of different generation. Now we will see there are few results, few important results are there. 6 results are there. That is very much important. First one is gene frequency of male. Gene frequency of male is equal to gene frequency of female. Gene frequency of female in previous generation. What is this meaning? If I write our offspring, so this will be gene frequency of male. Okay, and what will be the gene frequency of female in next previous generation? That is Q prime double X. Okay, so I can make arrow that this will determined by this, and this will determined by this, and female is determined by, and this is determined by both the parents. Like I make this. So I can say that this gene frequency of male is gene frequency of female in the previous generation. Similarly, I can write Q prime X is equal to Q double prime double X. Okay, like this is determined by female of previous generation. Now you can prove this also by using this frequency, like this R plus S, T and S or in the next generation. I'm not going to prove this results. Second result is, so we can say that male is completely determined by female. Second result is female offspring determined by both what? Sperm and egg. So gene frequency of female, gene frequency of female will be simple average of male and female. Okay, of the male and female frequency of previous generation. So this will be, now this is my QXX. QXX is what? The female of offspring, this female of offspring. Then this will be this will be determined by both the male and female of the previous generation. Okay, so I can write for the parental generation, Q prime double X is equal to half Q double prime X plus Q. So this is for offspring generation, and this is for parent. So these are my grandparents, and this is parents. Okay, are you getting the point? Now till this second property I will stop here, and we will continue tomorrow because time is almost 7:40. So is there any doubt, you can ask me in this today's class. किसी को कोई डाउट है, किसी को कुछ पूछना है? There are 4 more properties, we will cover it tomorrow. So with this we can make some results regarding this gene frequencies of parental, grandparent and offspring. Okay, किसी को कोई डाउट नहीं है, so I am stopping here. Okay then.